Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. It's my pleasure to introduce Rohit Khandekar. He's from IBM. He's been a researcher there for the last couple of years. He took his PhD from IIT Delhi, from where I did my undergrad, so he got more out of it there. And also at IBM, I just did an internship there. And here it is.
Thank you, Kamal. Really glad to be here. So I'll be talking about some recent work that I did with Baruch Awerbuch. It's on stateless distributed gradient descent for positive linear programs. And for those who don't like complicated titles, I'm essentially going to give a very simple and fast converging algorithm for solving certain families of linear programs. So let me start with the motivating example. It's one of distributed flow control. So you're given a flow network, it's a graph with the edge capacities, and you're given a bunch of commodities where each commodity corresponds to a fixed path in the network. So the red commodity wants to flow along this fixed path from this node to that node, the blue commodity wants to flow along the blue path, and so on. And your objective is to maximize the total profit you accrue by routing the flow subject to edge capacity constraints. More precisely, think of BP as profit you accrue by sending unit flow along path P, and FP is the flow you're going to send along path P. So you want to maximize the total profit subject to the constraint that the total flow through any edge is at most its capacity. Now this is an instance of a packing linear program. It's a linear program, and if explicitly given, there are many algorithms to solve this. But the model that we are going to look at today is somewhat more restrictive, and let me begin by describing it. So we assume that there is an agent associated with every path, and that agent decides how much flow is going to get routed along that path. But these agents have limited information about the instance. They don't know the entire network. They don't know the entire. They don't know how many other paths are there in the network. They don't know what are their individual flows. All that they can see at any point is the edge congestions on the edges on their own path. And just based on this information, they are supposed to update their flow values. So our question is,
but what is the goal of an individual agent?
Okay, so these individual agents are going to follow some prescribed protocol that you give them, and we want to design a simple protocol such that when these agents act according to the protocol, they together converge to a global optimum solution. So there are no game theoretic issues here, right? So these agents are not greedy, they don't have their own objective function.
Issue how to incentivize the agent to follow the protocol.
Right, so that will be another question, yeah. But here we are not looking at game theoretic issues. We just want to, these agents are faithful to follow whatever you tell them to. The main question is,
tell me where we can find these agents.
we'll take that, we'll discuss that offline. So the question is, can these agents achieve this global optimum solution just by looking at this local feedback that they get from the system? And moreover, we want the protocol or the algorithm to be stateless and self-stabilizing. So we really want the routing, the decisions that these agents take just depend on the current flow situation. They should not store any history about the past execution. And such a thing is useful, especially in a distributed system where things are not robust. If the edge capacities change over time, or the instance changes because some new agents come into the system, you don't want the algorithm to start from 0 or start from a well-defined state. You just want to start from the current situation, and this agent should be able to update just from the current solution and converge to a near optimum solution to the new instance. Now, as I said, the flow control problem was really an instance of a packing linear program, and we can in fact talk slightly in more generality about packing linear programs. So here is a linear program where we want to maximize a linear function c dot x subject to some packing constraints ax less than equal to b, and all the coefficients in a, c and b are non-negative, and we work with the same model. In particular, we assume that there is an agent j associated with every variable xj, and that agent knows the column corresponding to that variable. He knows the column j in the constraint matrix, and he also knows its coefficient in the objective function cj. And this agent is allowed to get some feedback from the constraints that he is present in. Say for instance, in this picture, this agent corresponding to this variable is present in these 4 constraints. So at any point, he is allowed to read off the so-called congestion values, namely aix over bi for the constraints for which aij is non-zero. And the question is again the same, just based on this local feedback, can he update his xj value such that these agents together converge to a near optimum solution quickly. So we will be interested in a fast converging stateless algorithm, and that's the main topic of this talk. So in the rest of the talk, hopefully I will be able to give you enough intuition and enough details about our algorithm. So before I start describing the algorithm, let me make some simplification. This is just to simplify the notation and make presentation really easy to follow. So this was the original LP that we are working with, maximize c dot x subject to some packing constraints. I am going to assume that the vectors c and b are vectors of all ones. All of their entries are 1. And that can be done without loss of generality by scaling. To make all b's 1, you have to scale the rows. To make all c's 1, you have to scale the columns. And we also assume that all the non-zero entries in A lie in the range 1 to A max, where A max is some real number. And we assume that these agents know the values of m, n and A max. M is the number of constraints, n is the number of variables. They need not know the exact values, it's enough to know some upper bounds. These values are used to set some parameters in their algorithm. Okay, so our algorithm is based on a primal dual complementary slackness conditions and how they imply near optimality. So let me briefly mention that. So this is the primal LP that we are trying to solve. Let's consider its dual. So we associate a variable yi with every ith constraint, and the objective in the dual is minimize 1 dot y such that A transpose y is at least 1. Now let's recall primal and dual complementary slackness conditions. So the primal complementary slackness conditions state that if jth primal variable is positive, then the jth dual constraint is tight. And similarly, dual complementary slackness conditions state that if ith dual variable is positive, then the ith primal constraint is tight. And it's very easy to prove that if x and y form feasible solutions to the primal and dual respectively, and then they satisfy, and if they satisfy both the complementary slackness conditions, then they in fact form optimum solutions to the corresponding linear programs. So our algorithm is going to try and make the solution x and y satisfy complementary slackness conditions. So that's the general goal, and eventually we'll be able to show that we obtain near optimum solutions. Okay, so with this intuition, let me describe the algorithm. The algorithm is really very simple to, it fits in a single slide and it's very simple to follow. So we start with any solution x that satisfies primal constraints. So start with any x greater than or equal to 0 such that ax is less than or equal to 1. And now I am going to repeat, every agent is going to repeat some execution. So in every round we associate dual variables yi corresponding to the primal constraints, and essentially yi capture how tightly the corresponding primal constraints are satisfied, right. So if ith constraint is very tightly satisfied, namely aix is very close to 1, then the value of yi is going to be large. So let's understand this. So let's on the other hand assume that aix is very small as compared to 1. If the ith constraint is very well satisfied, then this quantity is going to be negative, and I'll give you the values later, but mu is a large constant. So if this quantity is negative, then yi is going to be very close to 0. On the other hand, if aix is equal to 1, it's tight, then this is 0, so yi is going to be 1. So the whole point here is that yi capture how tightly the corresponding constraints are satisfied in the primal. Larger the yi, tighter is the constraint. So you can think of yi as also importance of the primal constraints. So if some constraint is very tight, then it's very important for me to focus on it. So yi gives a high weight for that constraint. And then every agent j is going to do some simple update on its variables. So what agent j does is as follows. So it computes the value of aj transpose y. Remember, the dual constraints were aj transpose y greater than or equal to 1, right. So the jth agent is essentially computing the value of jth dual constraint, and is going to compare that value to 1.
The ith agent from the matrix A knows the row or the column?
So the primal agents are indexed by j, and so we have a primal variable xj, and there is an agent j
Agents for
each column.
primal and for each dual variable, two agents.
No, we have agent just with primal variables. There are no agents with duals. We only get some feedback from the system corresponding to the constraints.
But my question is, does the ith agent know the ith row or the ith column of the matrix?
So ith agent knows the ith column of matrix A.
I see. But aren't you using both the column and the row here?
No, so okay, so aj transpose y really indicates the jth entry in A transpose y. So this is aj transpose aj transpose is really the jth column of A.
That's like the dual constraint corresponding to the
Right, so that's the dual constraint corresponding to the jth primal variable. So if you let's go back to the
Column. Aix is also aix is not the ith row times x.
aix denotes yes. So there is So aix denotes the ith. Ai denotes the ith row.
I see, but he knows aix. Okay. So he knows something about.
So
feedback from the system.
right, right. So he knows the values of aix over bi for the constraints that he is present in, and he knows the jth column. Right. So what does agent j do? He computes the value of the jth dual constraint, namely aj transpose y. So this is essentially the dot product of jth column of A with y, and he's going to compare that with 1. If this value is much smaller than 1, then he's going to increase his variable by a small multiplicative factor. On the other hand, if this value is much larger than 1, then he's going to decrease his value by a small multiplicative factor. And we need we need to have some additive change here, because if xj is 0 to begin with, then just multiplicative change will not be enough to change xj. So just to bootstrap that multiplicative change, we have this additive small delta. So what's happening here? Let's try to understand. In the flow maximization problem, we have agents associated with paths, and yi's are associated with the edges, right? So AIX denotes the total flow on edge I, and 1 corresponds to the capacity of edge I, right? So if the flow is very close to capacity, then the dual variable associated with an edge is going to be very large. So think of yi as the length of edge I, right? So if the flow is very close to the capacity, then the length of edge I is going to be large, right? Now what does agent corresponding to path j do? He computes the length of path j under this length metric, and if this length is small, then he thinks that there is enough space for pushing more flow. So in that case, he updates his flow by a multiplicative factor. On the other hand, the length of his own path is much larger than target length 1, then there is perhaps too much congestion on that path. So he reduces his own flow. Right? So it's easy to verify that an agent J just needs to know the values of yi for the constraints that he is present in, for the constraints for which aij is non-zero, because he just needs to know the value of this product aj transpose y.
Do you maintain a feasible flow during the process, or it could be feasible?
Yes, we will prove in a minute that the flow always remains feasible. So under these updates, for appropriate values of these constants mu, alpha, beta and delta, the solution x, the primal solution x, always remains feasible. You always satisfy ax less than equal to 1. So that's the entire algorithm. So start from any feasible point and just make these updates. And we'll show some nice properties about this algorithm. So any questions regarding the algorithm? Okay. So what do we show? What is the main result of our paper? We show that this algorithm starting from any feasible solution x. The algorithm always maintains feasibility, primal feasibility, x less than equal to 1, and converges to a 1 plus epsilon approximation in number of rounds that is polylog in the size of the LP and 1 over poly in epsilon. Yes?
The math looks very much like a formalization of Sutherland's paper, A Futures Market in Computer Time, is it?
I'm not aware of that work.
It's a classic. He divided up time on a PDP-1 computer. Guess how long time ago it was? By playing with prices per hour.
I see.
Look it up on the web. Fine.
Sure. Thank you.
No worries.
So starting from any feasible solution.
He didn't prove anything about that. He didn't prove anything, but in one university where I put this article on the boss's desk, it was implemented on Monday, and by Wednesday it was stable as a rock. Of course, that's anecdotal evidence. It didn't prove anything. Sorry.
Right. So we show that this algorithm converges to a near optimum solution in polylog number of iterations. And as you can see, this algorithm just depends on this local feedback that every agent needs to know from the system, and that's why it can be distributed. It can be implemented in a distributed manner if there is such a feedback available. And moreover, this is self-stabilizing because we start from any feasible solution. So as soon as the instance changes, there is a very easy rule to make the current solution feasible for the new instance by in a single step. And from there on, you can just run with this algorithm and converge to a near optimum solution quickly.
So if you are non-feasible, you have to do a pre-processing step?
Yes, it's actually very easy to do pre-processing step. So let's say if you know if any variable is present in a infeasible constraint, then he can just set its value to 0 in one step.
Or 0 is feasible.
So right.
No, but then you don't want to start.
Right, you don't want to start from all 0. So you should set your value to 0 only if you're part of an infeasible constraint. So that's why, I mean, if the whole point here is that if the instance changes in some part of the system, you don't want everyone to start from 0. You want the system to kind of self-adjust itself, and the effect should travel to the rest of the system slowly.
I missed how you pick delta?
Delta is set to delta is sufficiently small that increasing variables by additive delta should not affect system too much. And to set these parameters, the agents need to know the values of m, n, and a max. That's the only place where they use the information about size of the network. So I like to think of this algorithm as a combinatorial interior point method, because starting from any point inside the feasible region, the algorithm takes an internal path and converges to a near optimum solution in polylog number of iterations. Okay, so let me say a few words about previous work on combinatorial algorithms for solving linear programs. So there indeed has been a lot of work on designing combinatorial algorithms for packing and covering linear programs, and most of those algorithms are not stateless. So say for instance in Plotkin-Schmois-Tardas, Gerk-Könemann, Luby-Nissan, the algorithm set starts all the variables from 0 and then increments some it maintains some global information and increments some selected set of variables. The only work that I know of which is truly stateless is the work of Gerg and Young in Fox 2002, where they designed an algorithm for a multi-commodity flow problem with fixed paths. So essentially the flow control problem that I mentioned, and they thought of flow as injecting. They thought of flow as a stream of packets injected at the source, and the only feedback that they could receive was the total packet loss rate end to end. So the packets traveled through the network, and if some edge is more congested than it should be, then a random fraction of the packets were dropped. And the agents can read off the values of the total end-to-end drop rate, and just based on that information, they updated the congestion rate, the packet ingestion rate. So they showed convergence to 1 plus epsilon approximate solutions in time proportional to C max, where C max is the maximum objective coefficient. And it was not clear how to generalize this algorithm for arbitrary positive linear programs. So you can think of our algorithm as somewhat extending this work to arbitrary linear programs and also improving the convergence rate.
But your feedback is different.
Feedback
From than they do, right?
Feedback is somewhat related because so the end-to-end drop rate is actually related to the total length of your path if you associate exponential length function with every edge. So there is some connection, although it's not an explicit.
As you stated, you need to get feedback from each edge. As you stated in that.
No, actually a path just needs to know the total length of the path. We don't need separate lengths from the edges, because we compare the total length of the path with 1, and if the path length is small, we increase the flow. If path length is larger than 1, we decrease the flow. So we just need to know the aggregate path length. Right, so on this slide I've briefly mentioned the key differences from previous work. So most of the previous algorithms, as I mentioned, start from 0 and they only increase the variables. And they maintain some global threshold information and increase the variables that are better than the threshold. On the other hand, we start from arbitrary feasible solutions. And since we start from arbitrary solutions, we need to have an ability to both increase and decrease the variables if we want to achieve near optimality. And we are stateless. We don't maintain any state information, or we don't need any initialization. But they have better convergence dependence on epsilon. So I think it's 1 over epsilon square, while our convergence is only, we could show only a 1 over epsilon to the 5 convergence. Okay, so let me go and give you some intuition about the analysis. So let me quickly argue that algorithm always maintains feasibility, primal feasibility throughout the execution. So to prove this, we show that all the yi's are at most 1. And if all the yi's are at most 1, then it follows immediately that aix is less than or equal to 1. Now suppose not. Suppose some yi increases to more than 1. Now for that to happen, some xj with aij greater than 0 must increase to make yi larger than 1. But for xj to increase, the value of aj transpose y must be less than 1 minus alpha from the definition of the algorithm. Only then can xj increase. But all the non-zero entries in A are at least 1. And in particular aij is at least 1. Therefore yi must be less than 1 minus alpha before this increase. Right, so yi is sufficiently smaller than 1. And now comes the trick. So we set the parameters beta, namely the step length parameter, the multiplicative increase by which we update the variables beta, small enough so that any yi changes by a very small multiplicative factor. More precisely, we proved that yi changes by at most a factor of alpha over 4 in any single round. So if yi is less than 1 minus alpha to begin with, no, multiplicative, 1 plus alpha over 4, right? Changes by at most a multiplicative factor of alpha over 4. So if yi is less than 1 minus alpha, then in a single round it cannot be more than 1. So in a sense, the point here is that we have to set the step length parameter small enough if you want to maintain feasibility. But you should not set it too small because you want fast convergence. So that will come next. Now another quick point that we should verify before proving that the algorithm converges to near optimality is that the fixed points of this algorithm are indeed near optimum, because the fixed points are fixed points and they better be near optimum if your theorem is true. So let's quickly show that. So let's take a pair of solutions x and y. X is the solution and y is the corresponding setting of dual variables, and assume that x comma y is indeed a fixed point of our algorithm. We'll show that x and y both correspond to near optimum solutions to primal and dual respectively. So first let's show approximate feasibility. Since x is a fixed point, no xj is changing, therefore the value of aj transpose y for every j is between 1 minus alpha and 1 plus alpha, right? So all the dual constraints are not only approximately satisfied, they are very tight. All the dual constraints are tightly satisfied. And in fact, in the previous slide we already showed that x is always feasible. So primal feasibility is already established. So we have that both x and y are approximate feasible. Now we argue that the complementary slackness both the complementary slackness conditions are satisfied in approximate sense. More precisely, if xj is large, then the jth dual constraint is approximately tight. Well, we just argued that all the dual constraints are approximately tight. So the primal complementary slackness conditions are trivially satisfied. On the other hand, if yi is large, then from the definition of yi, the ith primal constraint is approximately satisfied, right? Because recall that yi was a very fast growing function of how tightly the constraint was, the corresponding constraint was satisfied.
This is true for all solutions, x point or not, right?
Yes, this point is actually true for all x and y. And if you put these two things together, we can argue that x and y actually form near optimum solutions. So the fixed points are actually near optimum solutions to both primal and dual. But since our goal is to not just analyze fixed points but to show fast convergence, we need some measure of some potential that we can track and prove that we are making significant progress toward optimality in every step. So to this end, we
Can you go back once?
Sure.
The only place where this is a fixed point is the feasibility of the dual, or is it somewhere else? Where is the property that it's a fixed point being used beyond it being the solution?
I guess we only use it here. That's right. Approximate dual feasibility. That's right. So to show fast convergence, we have to have some monotone property of the algorithm, because the variables are going up and down. So it's very hard to track what's happening in the system. So that's why we looked at this particular potential function, which is essentially the primal objective function summation xj minus a penalty for violating primal constraints. So recall think of yi as penalty for violating the ith constraint, right? So you get profit by routing more flow, but you get penalized for violating edge capacity constraints, right? And in fact, to give some intuition about this potential, I tried to plot So let's consider a very simple linear program which has two variables, x1 and x2, and the linear program is maximize x1 plus x2 subject to the constraint that x1 is less than equal to 1 and x2 is less than equal to 1, right? So what's happening here is that I've plotted, so this is x1, this is x2, and along the z-axis I've plotted the potential function. So the potential function increases with x1 and x2, but as we come close to the boundary of the polytope, the penalty shoots up and the potential function dips to minus infinity. Right? So as you get closer and closer to the boundary, the values of yi increase so rapidly that that it starts penalizing. So the maximum point of the potential function, which is here, is actually very close to the optimum solution, which is at this vertex, right? Because as long as you are far from the boundary, you are doing the same thing as the objective function does, but when you go close to the boundary, your potential function dips, right? So what we show in our analysis is that our algorithm actually is working in hindsight with this potential function, and this potential function only monotonically increases during the algorithm. So analytically, this potential function has some nice properties, and this is what the next equation shows. So first of all, note that this potential function is a differentiable function of variables xj. It's not only continuous, but since yi are exponential functions of aix minus 1, it's actually very smooth and you can differentiate. So if you look at the partial derivative of the potential function with respect to jth variable, and if you plug in this expression and simplify, then it turns out to be equal to 1 minus aj transpose y. So this is the gap, this captures how tightly the jth constraint is satisfied, right? And if you recall, the decision of whether to increase xj or decrease xj was actually based on this quantity, right? So if you approximate the change in the potential by the first order terms, namely the change in xj values times the derivatives, then you can show that this quantity is in fact always positive, non-negative, because you increase xj only if this is positive and you decrease xj only if this is negative. So this is the basic reason why the potential only increases. And moreover, we can say something stronger. Recall that we increase xj only if this is significantly larger than 0. This is at least alpha. And we decrease xj if this is at most minus alpha. So overall, the increase in the potential is at least alpha times the absolute change in the x values. Right? So if x values are changing rapidly, no matter whether they're going up or down, if they're changing rapidly, you're making progress with respect to the potential. And that's why you can think of this algorithm as doing distributed gradient ascent on this potential. Okay, so how do we show fast convergence? So we just noticed that a significant change in x values leads to a significant increase in the potential. And similarly, you can show that a significant change in y values leads to significant increase in the potential. Because intuitively speaking, y values are determined by x values. So if y values are changing rapidly, then x values are also changing, and that's why the potential function increases. But the potential function is bounded. It cannot always increase. I mean, it cannot increase without bound. So such a thing cannot happen forever, right? So it cannot happen that x and y values are changing a lot for a long time. And then we show this important lemma that says that if x and y values do not change significantly in an interval of appropriate length, then we have near optimality. Epsilon is the error parameter that, so we are achieving a 1 plus epsilon approximation. So more precisely, if we take any interval of logarithmic number of rounds, and if you notice that throughout the interval the x and y values did not change by too much, then we show that x and y, x solution x throughout the interval is actually a near optimum solution to the primal. So let's call this a stationary interval, an interval of logarithmic length where x and y values do not change. And on this slide I have tried to show you an intuition of the proof why stationary interval implies near optimality. So consider a stationary interval and consider any x in that interval. Now if x is not near optimal, then we show that there exists a variable xj such that aj transpose y is consistently less than 1 minus alpha throughout the interval. And if such a thing holds, then from the definition of the algorithm, xj will be increased multiplicatively throughout the interval. But since length of the interval is logarithmic, xj will become more than 1 soon, which would contradict the feasibility that we have already shown. Right? So the key point here is that assuming that we are not near optimal and assuming that the x and y values are not changing rapidly, there indeed exists an xj for which this property holds, right? And the proof of that fact is also easy. It's essentially 4 lines, but the intuitive reason is that if we're very far away from optimality, then there must be some variable xj that optimum solution is exploiting that you are missing on, and that is the variable that you should focus on. So that's the intuition, but more precisely, let me just walk you through this chain of equations. So let's say x star is the optimum solution. From our assumption that x is not near optimum, we know that 1 dot x star is much larger than 1 dot x. These are the objective values. Now since x values are stationary, all the aj transpose y's are approximately equal to 1. So this is roughly equal to this. But since y is a fast growing function, most of the mass of y is concentrated on those constraints for which aix is roughly equal to 1. So that's why this is approximately equal to this. And since ax star is at most 1, x star is an optimum solution, so it satisfies the constraints. This is at least y transpose ax star, right? So in a nutshell, what we get is that 1 dot x star is much larger than y transpose ax star. Now think of this quantity as an average of values aj transpose y under the weight x star j, right. So this divided by this is the average value of aj transpose y, which is much less than 1. So in particular there will be a variable xj for which aj transpose y is much less than 1. So of course this is just an outline, the details are given in the paper. So let me summarize. So we just saw a very simple stateless and gradient descent based algorithm for packing linear programs, and a very similar algorithm also works for covering linear programs, where the objective is to minimize c dot x where x greater than or equal to b. Mixed packing and covering, the positive linear program where we have both packing and covering constraints, and some convex programs where the objective is let's say we want to maximize some concave function of x's subject to some packing constraints. Like in flow control, instead of maximizing the total flow, if you want to maximize some fair objective function like log of the flows, then you can use similar ideas. The main open questions that I would like to know answers to is, what happens if the linear programs are not given explicitly? Let's say in multi-commodity flows, if the paths are not fixed, then it's an implicitly given LP because there is one variable for every path. So can you implement this algorithm in a compact way so that the running time remains polynomial? And of course look for other applications of this simple update rule. Let's say for market equilibrium questions, can we compute market equilibria using such algorithms? I'll stop here. Thank you for your attention.
So you talked about the convex program. Did you talk? I mean, market equilibria is a convex program. The only difference is the objective function instead of additive, the objective function is multiplicative.
So what we use crucially in this analysis is the positiveness of the packing linear programs. So for instance, I don't know how to generalize this to arbitrary linear programs even.
No, but the constraint in market equilibrium are the same, the packing constraints.
Are packing constraints.
Yeah, the only thing difference is the objective function. Instead of saying the objective function is a summation ai xi, it is summation ai log xi, or you can interpret it as a multiplication xi's to the power alpha i's.
Right. So if the objective function is, so we are trying to maximize the concave objective function. Subject to packing constraints, yes. So I think for that it should work too. Although we have to be careful regarding what kind of approximate solutions are we computing, because we may be computing a weak approximate market equilibria.
Let's say you're approximating this convex program.
Right. I think some algorithm like this should work, because all that we are really using is convexity of some potential function, and basically doing gradient descent on that.
So somehow another way to look at it is you're taking a constraint optimization and converting it into non-constraint optimization.
Right. Adding a penalty function for violating constraints.
But the other part is somehow by doing this you're also getting this monotonicity of potential.
Right, so I really think that there is scope for extending this work to other more general mathematical programs.
Also, could you go back to the slide?
This
No, the open problems. So what is the main difficulty in this implicitly given tracking instance?
So here, so our algorithm maintained a separate agent for every variable, and and an agent is updating his own variable value. So here you would like to associate an agent with a commodity, a sourcing pair, and not with every path. So if you kind of try to implicitly update all the flow variables by not doing this exponential amount of work, but try to just do polynomial amount of work, then at least the initial calculations run into some problems. So another question is, can we modify the update rule to make it more smooth and then give an implicit way of updating all the flows along the exponential paths implicitly?
So somehow, your update rule depends on the length of the path, right? So
Right.
I can calculate all the lengths of the path. I can calculate the
Could be
shortest
exponential number of paths.
But there are exponentially number of paths. So, and you don't want to maintain flow values for every path. So we have been able to show some results in this direction. More precisely, if the path lengths are bounded, if let's say I allow you to send flows along paths of length at most h, then we can get convergence which is polynomial in h. So instead of polylog convergence, we can show that we converge in like h square number of iterations. So there you don't have to maintain, you just maintain the flow, not the flow path decomposition, and then you update the flow along short paths in your flow. But I don't know how to show this for general and to get, more importantly, to get poly-logarithmic in n convergence.
Also, suppose we change, we complete some solution. Now we change the constraint metrics like A a little bit. Since you allow axis to start from arbitrary point, then we should be able to move axis x quickly to the new optimum. So did you look at that?
Right, that's a good question. Yeah, I have been asked that question before. I don't know how to show fast convergence which is better than this for starting from a near optimum solution. Right, that's a nice interesting question. I don't know how to show that yet.
Thank the speaker.
Thank you.